Okay, this is the second video on titrating a weak acid. In the first video we talked about finding the pH along the first 2 points in the curve. So you have your initial pH where it's pure weak acid. Just use an ice chart, use your Ka value to solve for your H plus concentration, then take the negative log of H plus to find your pH. If you're here at point 2, where you're some point along the curve before equivalence, then first you have to figure out how much HOCl, so how much weak acid do you have left over, how much conjugate base did you create, and that's just a stoichiometry problem where you look at moles, doing some subtraction, some's going to get used up, some's going to get made, and then once you have those values, you can plug that into a Ka expression and solve for pH, or you can also use this equation down here. Again, as long as you're somewhere in this middle part of your titration, this equation is okay to use as well. Alright, I'll wait for the bell. The next point I want to talk about, point 3. This is if you're at the halfway point. So when you're exactly halfway to equivalence, what happens is, we started with 1 mole of your weak acid. At the halfway point, you only have half a mole of weak acid left. Half of it has been used up, and you've created half a mole of your conjugate base. So you'll notice our concentration of weak acid is equal to your concentration of the conjugate base at that halfway point. So if you look at this equation, if A minus equals HA, this value is 1, and the log of 1 is 0. So that means that at the halfway point, the pH equals the pKa. So in this case, at this point along the curve, to find the pH, I can just take the negative log of the Ka value. And the Ka value in this case was 3.5 times 10 to the negative 8th. If you take the negative log of it, you will find that your pH is around 7. And again, if you want to know how you can do that in your head, just guesstimating it, if you're trying to take the log of this number right here, it's going to be a little bit less than this value. So if it's 3 times 10 to the negative 8, my log of that's going to be around 7-ish. The log of this value right here is going to be around 6 point something. So just keep that in mind. If you plug in your calculator, I believe you find that the pKa is 7.5 at this point. So at the halfway point, my pH is 7.5. pH equals pKa. All right, how about when we get to equivalence? At equivalence, that means that, notice in this case, equivalence happens at 1 liter, because I'm titrating 1 liter of 1 molar HOCl, so basically a mole of HOCl, with 1 molar NOCl. So I will reach equivalence when I have added 1 mole of NaOH to my 1 mole of HOCl. So it's when your moles of your strong base that you add is equal to your how many moles of weak acid you initially had in your reaction. So that means all of my weak acid will have been used up and will have been turned into the conjugate base. So what you have at equivalence is a solution of pure weak base. So let's talk about finding the pH there. If you have a weak base, you want to say, okay, weak base, when I stick it in water, it's going to be a hydrogen taker. So bases are hydrogen takers, acids are hydrogen givers. If I show my base in water, it's going to take a hydrogen from water, creating HOCl and OH minus. This is my equilibrium system. I can write a K expression for it, products over reactants. I will call that K expression a KB expression. And if we fill in this ice chart, first I want to figure out what your concentration is. So I know that I have added, so look back at this titration reaction. I started out with 1 mole of HOCl, and I added 1 mole of hydroxide to it. So at equivalence, these have all been used up and converted into OCl minus. So at equivalence, instead of, I started out with 1 mole of HOCl, now I have 1 mole of OCl minus. All of this has been turned into this. So I have 1 mole of OCl minus at equivalence, and I want to consider what my volume is. So I started out with 1 liter of solution. I had to add another liter in order to get to equivalence, so now my total volume is 2 liters. So my concentration of my weak base is 0.5 molar. I'm going to ignore water because it's a pure liquid. These start out at 0. And so I'm going to use my ice chart. I'm going to say this can go down by some value x, this will go up by some value x. And at equilibrium, I have 0.5 minus x, x, x. So Remember, we can describe this equilibrium using a Kb value, but the problem only gave us a Ka value. So what you might need to do is something like this. Use the fact that the Ka times Kb for a conjugate acid-base pair will equal Kw. So I can find the Kb for this reaction by taking Kw, which is 1 times 10 to the negative 14th, and dividing it by my Ka value, which was 3.5 times 10 to the negative 8th, and that will give me my Kb value, 2.9 times 10 to the negative 7th. So Kb equals x squared over 0.5, my products over my reactants. And if I solve for x, keep in mind x in this case is giving me a hydroxide ion concentration. So this is my hydroxide concentration. If I take the log of it, it will give me the POH. So to find the pH, I just take 14 minus the POH. So my pH at equivalence is 10.58. So I've got a relatively high pH, okay, because I have a solution of weak base at that point. If you want to figure out the pH after equivalence, you can say, well, how much hydroxide do I have around? So after equivalence, you've got the weak base present, and you're going to have some excess hydroxide. So in this case, if we think about what we did, if I want to try and find the pH at this point right here, when I've added 2 liters of 1 molar sodium hydroxide, I can say, well, 2 liters of 1 molar NaOH means I added 2 moles of NaOH. Some of that NaOH reacted with my acid. And remember, I started out with 1 liter of 1 molar acid. So I started out with 1 mole of acid. And so basically what that means is, at this point, some of my base has been used up. So I started with 2 moles of base. A mole of that reacted with my acid. So what's going to be left over is I'm going to have 1 mole of sodium hydroxide in excess. So I have some excess sodium hydroxide floating around. So the pH at this point is going to be determined by how much excess hydroxide ions I have around. So I've got 1 mole of hydroxide ions, and my volume at this point is my initial 1 liter plus the 2 liters that I've added. So my total volume here is 3 liters. So if you were to look at that, that is what, 0.33 molar hydroxide. And if you were to take the negative log of that and subtract 14 from that, you will find that the pH ends up being 13.5. That being a pretty high pH. You've got lots of excess hydroxide ions. You're not as likely to have to calculate this, but I thought I would just add that in there as something to consider. So just to summarize, initially, when you're finding the pH, you're going to use the Ka value. At equivalence, you're going to use the Kb value, and keep in mind what you have is the conjugate base. If you're somewhere in between, you've got both the weak acid and the conjugate base. So at that point, you could use pH equals pKa log A over HA, or you can also use your ice chart and the Ka value to solve it as well. Either one of those methods would work. And if you were titrating a weak base with a strong acid, everything would just be the opposite. So you'd be starting out with a Kb value. At equivalence, you'd be dealing with a Ka expression. Anywhere in between, you could still use the same equation right here. And if you're after equivalence, in that case, rather than having excess hydroxide around, you'd end up with excess hydrogen ions in your solution. So, yes, titrations.